Hey everybody, and welcome to this video about recursion. So what is that? What is recursion? Well, it's like dreaming about your dream, and when you wake up, maybe you're still in that dream, as it states in the meme. But in other words, it's also a programming technique that is used to solve many problems in computer science. And technically the definition is when a method or a function or procedure calls itself, it is called recursive. We have a simple example. There is no return here. We just have a public static function countdown, and we can see that we have a counter. We have a system out print line. It is Java, and as long as this counter is more than 0, we're gonna call the function itself with a parameter that is the counter minus 1. So that is the recursive call here. So that's going to produce 5 and 4 and 3, 2, 1. So that's a really simple recursive call here. And we don't have any return, because you can also create recursive methods that will have a return, and that is the case in many recursive methods. Another example here is when we have recursion, and we also have a return type here, and we also have some base cases. This is a function that calculates the factorial. That is a math term, and in this example we can see that if we are, well, the factorial is kind of 1 times 2 times 3 times 4 all the way up there, and it can produce really high numbers. And we will have a base case stating that when n is 0, we will backtrack. So we're going to return 1 here. But if it is higher, we're going to call factorial recursive with the number, and then with the number minus 1. So if we have 2, for instance, we're going to call 2 times factorial recursive and then 1 here. So that is going to also produce a recursive result here, and then we have the base case. And in a lot of algorithms, there need to be a base case where we can actually backtrack. We can return a simple case, because we cannot continue indefinitely just by calling recursive here. We need to have a base case. Yeah, and when you have a recursive call, it is possible to convert it to an iterative, meaning that you can go from having this recursive call to actually use a normal loop, a for loop in this case. So this is the same algorithm, but it solves the problem in another way. It doesn't use the recursive call here. It uses a normal for loop where we basically run through all the different numbers, and then we calculate it by doing the product multiplied with I. So that is basically the same we do here, but we're not doing any recursive calls. And that is the case with many recursive algorithms, that you can convert them into their iterative counterpart there. So why should we use recursion in the first place? Well, there are examples where if we need to, let's say we need to search in an array or in a list or something like that, that it can become really handy to use recursion. This is a binary searching illustration here, and we can see that we have the time complexity up here stating big O log n. And this is a good time complexity because it will, normally we say that if we can keep the time complexity under n raised to the power of 2 or something, it is acceptable. I know that there are a lot of problems that require us to use algorithms that will have nested loops, 2 or 3 or 4 loops inside of each other, but it really impacts the performance of the algorithm. So this algorithm here, we can see that it will actually divide up each portion of the array, and then it's gonna call the function recursively with this portion here. So we have the left side and we have the right side. And we can see this in the code here really quickly, that we have binary search, we have an array, and then to get the overview, we're calculating kind of the middle, the median value, and then we run the same function, recursive call, with the left side and the right side. So we are actually making a lot of calls with the same function. And again, we have the base case. If key equals value, we will return the base case. We will backtrack. Then we have a term called divide and conquer. And what is that? We can see this is quicksort, a fast sorting algorithm that uses recursion. Divide and conquer is a programming design paradigm. And what does that mean? Well, it means that we will divide our problem area, our array collection, whatever we have, into subproblems. And then we will solve each or conquer each subproblems with the same method. So in this example here with quicksort, we're going to divide up our array, and then we will run quicksort on each of these subproblems. And again, we will, with these two, we're going to divide them up and run recursively with quicksort. So again, we will get this better time complexity typically than we would if we used a traditional approach with nested for loops maybe inside of each other. Because if you compare this with bubble sort or insertion sort, something other than that, then the time complexity for this is better. And yeah, we can see how the quicksort works. I'm not going to go into details with this as it's more like of a sorting tutorial. We also have the other way, merge sort, where it's doing the same thing, but we're doing another approach where we are merging the arrays into one. Okay, so that was sorting and searching with recursion. We also have other problem domains where it can be useful to use recursion, and one of the prime examples of this is the Tower of Hanoi. And basically the problem is about that we have 3 towers, and then we have a certain amount of disks, and then the rules state that we should get all the disk moved to tower C, but we cannot put a disk that is bigger than the other disk on top of each other. So we can't put bigger disks on top of each other. We need to use the tower B kind of as a temporary place there. So we can use a recursive strategy to solve this problem. And the recursive strategy is put down there. I'm not going into detail exactly how we're going to solve this, but you can see the function here right now, and we can see that we have the function move, and then we actually do a recursive call with parameters here, and we can see A, B, and C. That is for the different towers, and this will actually solve the Tower of Hanoi. And this is not log n or linear time or n raised to the power of 2. This is exponential time. So if you increase the amount of disks, it will increase the amount of moves exponentially. So that is really, really tough on the performance of the algorithm. So not all cases of recursion is gonna give you a nice time complexity, but this will give us a nice solution that looks pretty compared to the iterative one maybe. This was basically what I wanted to talk about using recursion, and you can try out some of these examples in Java or another programming language. Alright, thank you for watching, and I hope you make this work. Bye bye.